Here we have y equals e to the x cosine x, and we're going to just graph this for a limited domain from negative pi to positive pi. So we don't really need to know the endpoint behavior, but we do need to know the endpoints. So first thing we're going to do is we're going to plug in our values here for the endpoints of negative pi, and we get approximately negative e to the negative pi. And that gives me a value of approximately negative 0.043, okay? And then we're going to plug in our value at pi, and we end up with e to the pi, which is approximately, negative e to the pi, which is approximately negative 23.14. So those are going to kind of go off that point's going to be off our graph, but we'll show that afterwards. So we have that. We're going to then solve for the zeros. The zeros are when the e to the x is never equal to 0. So cosine x is equal to 0 at 90 degrees and negative 90 degrees. So we have zeros at x equals pi over 2 and negative pi over 2 and pi over 2. So I'm just going to draw those in. I'm going to have those zeros there. And at negative pi over 2, negative pi over 2, we're going to have a coordinate at 0. And at positive pi over 2, we're going to end up with, I'm going to need to spread this out a little bit, but we're going to have coordinate at 0 as well. Okay, so I'm just going to move this down a little bit to give myself a little bit more space. Okay, so at pi over 2, we're going to have a 0 as well. Okay, so we have some points there. So what we're going to do is we need to then work out the derivative here. Okay, so differentiating this, we're going to end up with the derivative is going to be y prime e to the x cos x plus e to the x. The derivative of cos x is negative sine x. So we end up with y prime is equal to e to the x is one of the factors, and we end up with cos x minus sine x. Okay, so e to the x is never equal to 0. Now, solving this equation is a little bit tricky because we have a cos and a sine, but I'm just going to write it like this, cos x, and really we're trying to find out where cos x is equal to sine x when that's equal to 0. And solving this, I can rearrange this expression by dividing both sides by cos, and I end up with sine x over cos x. Now, we could have interpreted this equation here and just said, when are the sine and cos the same? It's going to be the same in quadrants 1 and 3 at 45 degrees and 225 degrees. But we can actually solve this algebraically as well if we convert this into sine over cos, because really that is equal to tan x. So where is tan x equal to 1? Well, we have a slope of 1 here and here. Okay, so that's going to be at pi over 4, and that angle down in quadrant 3 is, and we have to go in this direction, so it's going to be negative 3 pi over 4. So identify those coordinates at x equals negative 3 pi over 4 and positive pi over 4. So those points then I'm going to put into my table of values. So negative 3 pi over 4, when I plug that in, I end up with a value of negative e over to the negative 3 pi over 4 over root 2, and that's approximately equal to, as a decimal value, that's approximately equal to negative 0.067, okay? And then we plug in our positive pi over 4 At positive pi over 4, we're going to end up with e to the pi over 4 over root 2, and that works out to be approximately 1.551. Okay, so we've got some coordinates there, and we're going to start maybe plotting a few of these coordinates. So at negative 3 pi over 4, which is right about here, it's just down very, very close to the x-axis. So really, really close to the x-axis here. At positive pi over 4, so that's positive pi over here, it's going to be at 1.55, so about 1.5, somewhere up just above that line there. Okay, so those are some coordinates we have. We're getting an idea what this looks like, and we can see that as we get closer to the endpoint here, it's going to tend towards 0. And as we get closer to the endpoint on the other side at pi, we're going to go way off the graph. So it's going to go way down here. Okay, so we're going to look for then the second derivative of this. Okay, the second derivative of this, we're going to differentiate again. So we're going to take the second derivative, y double prime. When I differentiate that expression, I'm going to end up with e to the x times cos x minus sine x plus e to the x, and then differentiating cos, I get negative sine x minus the derivative of sine is going to be cos x, and then I can simplify this expression. I'm going to end up with the cos x's cancel out, so I end up with e to the x, and I end up with 2 negative sine x's, so negative 2, and then I'm going to write that as sine x here. Okay, so there's my derivative, negative 2 e to the x sine x, and I want to know where this is equal to 0, and that's going to be equal to 0. E to the x is never equal to 0, so we're looking for when sine x equals to 0. Okay, sine x is equal to 0 at 0 here and negative pi. Okay, so that's when we're going to have our inflection points are going to be at 0 and negative pi and also positive pi. So I'm going to maybe write that down. X is equal to negative pi, 0, and positive pi. Okay, so at those endpoints, we do have an inflection point. We're not going to show that, but that there will be or potential inflection points there. So plugging in x is 0 into my table of values, when I plug in x is 0 into my original equation, I get e to the 0 times cosine of 0, and cosine of 0 is 1. So there's another coordinate. So I know there's another point right there. And that point I know is an inflection point. So doing my slope chart here, I have negative pi over 3, so negative 3 pi over 4, and we have a 0 here. We have positive pi over 4, we have a 0 here, and we have to test our inflection at 0. Okay, so we have a 0 inflection here. So I'm going to start with my slope charts, and I'm going to test my slope, the y prime, at, let's try y prime at negative pi. When I plug negative pi into here, I get e to the negative pi, which is positive, and I get cos of negative pi, which is negative 1. Sine of pi is 0, so I get negative in here. So I end up, this is going to be negative slope. Okay, so I end up with negative slope here, so it goes down. It looks like that's a potential minimum point. Okay, I'm going to test the slope at 0. Plugging in 0, I end up with e to the 0, which is positive, cosine of 0, which is 1, and sine of 0 is 0, so I get positive 1 here, so that's a positive slope through this region. So this must be a potential maximum. So we're going to test another slope point. Let's try pi over 2. E is always positive. Cosine of pi over 2 is 0. minus sine of pi over 2 is 1, so I get negative 1 here. And so that's going to be negative slope through this region. Okay, so I have a potential min point that I have to test. So my candidate's list is going to include my endpoints. I've got a minimum point at 3 pi over 4. I've got a maximum point to test at positive pi over 4, and then an endpoint at pi. So these are points I'm going to have to check for my max min points. Testing my concavity, so the second derivative, let's try negative pi over 2. When I plug in negative pi over 2 into my second derivative, I end up with e is always positive, so I get negative 2 times e, and sine of x, ascend negative pi over 2 is negative, so I'm going to end up with positive concavity here. And again, my slope chart kind of confirms that that is true. My second derivative, I'm going to try positive pi over 2. When I plug that in, negative 2 times e is negative, and then inside the bracket, sine of pi over 2 is going to be positive 1, so I end up with negative concavities in this region here. Okay, so those are my slope charts, my concavity charts. I'm going to sketch this graph before we do our candidates, before we check our candidates. So just zooming in here, we know that it's going to come down like this. There's a minimum here. It's going to go through the 0. It's going to curve through here and then change concavity through this point. We end up with a max. We end up with a 0 here, and it's going to go way, way down. And at those endpoints, we will have the second derivative equal to 0. So there are potential changes in concavity at those points, but we don't need to worry about them because we're only going to graph from negative pi to positive pi. So then looking at our candidates list, I've kind of made a list here. So putting our values, negative 0.043, negative 0.067. We know that's a local min. At pi over 4, we have 1.551, and we have negative 23.14. Okay, so based on this, we know that this is my absolute min. Okay, so this is my absolute min. We know that this is our, oh, sorry, that's not our absolute min, that's a local min. This is our absolute min here. And then we can see that our local max is our absolute max.